In this video, I will explore an AC-C circuit, and C stands for the capacitor. So in the previous video, we had an ACR with a resistor. This time, we will see what happens when we have a capacitor connected to an AC power source. Now we can control, okay, I decreased a little bit the frequency to increase the period. Now let's see a little bit what happens on the capacitor. So when electrons are moving away from the capacitor, this becomes positively, from this plate, when they move away from this plate, this becomes positively charged. When the electrons move towards this left plate, then that becomes negatively charged, and that makes sense. In a similar fashion, when electrons are moving towards the right plate of the capacitor, it becomes negatively charged, and when they move away, this becomes positively charged. Now, because the electrons are going back and forth, right now this has a negative charge, but then positive, and then negative again, and then positive again, due to this oscillating motion of the electrons left and right, which again originates from the fluctuating potential difference of the AC power supply. So when you have a capacitor, when you connect it to an AC power source, the way that the plates of the capacitor are the plates of the capacitor are charged changes as a function of time. Now this is different than what we're used to. If we connect a capacitor to a battery, within 10 to minus 9 seconds, within time on the order of a nanosecond, the electrons are going to move from the negative side of the battery to this plate, and it's going to make this it will make it negatively charged, and then this is going to leave the right plate of the capacitor positively charged, because here electrons have moved away from it, and that's it. Compare that capacitor with this one. In an AC power source, the plates of the capacitor change polarity. One moment in time they are positively charged, the next they are negatively, and then positively again, and so on. So this is a feature of having an AC-C circuit, a capacitor connected to an AC power supply. Now, I also want to see how the potential. I'll bring this here. I'll have the current, the ammeter on the top, and the potential difference here. Let's see. So for the current, okay, this is the graph of the current as a function of time, the usual sinusoidal motion. So it reaches the peak, goes to 0, minimum, 0, maximum, and so on. And I will also measure the potential difference. What I want to do, actually, I want to change the way that I have this so I can illustrate how the current behaves. Okay, so if you look at only the potential difference versus time graph, it is also a sinusoidal graph. Now what I want to do here, if you remember in the ACR circuit, we had the current and the potential difference reaching the maximum and the minimum and the zeros at the same moment in time. This is no longer true in an ACC circuit. The current and the potential difference behave across the capacitor behave in a different way. So obviously when I have the maximum in the current, I do not have a maximum in the potential difference. Now let's see if we can... Okay, I'll use this moment in time. So look at the current. It just passed through the zero, and the potential difference just passed through the maximum. Now the current keeps decreasing to reach the minimum. The potential difference has just started decreasing. Okay, this is showing us that the current that flows here is leading the potential difference. And by leading, I refer to the current is ahead compared to the potential difference. And it is ahead, it leads the potential difference because the voltage here is at the peak, but the peak at the current took place some time ago. Okay, not just now. It was a little bit of time before this moment. So this reason, because the peak took place previously for the current, is telling us that the current leads the potential difference across the capacitor. Now, by how much? Okay, we know. Okay, let's look at this. So from here to this point, I have one period. Okay, the horizontal axis is the time axis, and I know that one period is the time that it takes to do one cycle. So if I start from here, one cycle would be this. Okay, start from here, go down, 0, maximum, back to 0. This is one period. Now, if since the potential difference is at the peak and the current is at this 0, then the current and the potential difference are off by 1/4 of the period. Okay, so from here to here is one period, from here to here is half the period, and then that means here I have half of the period. From the peak to the 0, I have 1/4 of the period. Now, we don't typically, so I could say that the current leads the potential difference by 1/4 of the period. We don't really use time to indicate by how much the current leads the potential difference. We typically use the phase, so it's going to be in terms of radians. I know that 2 pi is essentially 2 pi would correspond to one period, so 1/4 of the period would correspond to a phase difference of pi over 2. And that's why we say that the current leads the potential difference by pi over 2. Let me make some notes. So as I said, from here to here, I have a period. This would be one period. Then from here to here, I have the period over 2. And then from this 0 to that, I have the period over 2. And because when the current is at the 0, the potential difference is at the peak, I'm interested in looking at this time difference. And this is half of the t over 2. So this is 1/4 of the period. Okay. Now, as I said before, one period corresponds to a phase difference of 2 pi. So half the period would correspond to a phase difference of pi, and then 1/4 of the period corresponds to a phase difference of pi over 2. And that's why we say here, for an ACC circuit, the current leads the potential difference with a phase difference of pi over 2. This terminology we use for ACC circuits.